Welcome to Unit 2, Chemistry Stars. We're looking at Chapter 5 and 6 together. Learning the language of chemistry is known as nomenclature. I have my note pack out in front of me. You do as well. It has the title, The Periodic Table and Nomenclature. Let's begin by opening up to find that first page of our note pack as we begin the journey of naming and forming compounds. Now, when we learn a new language, we always start with small steps first. Just as if we're learning a new language, we have to learn the alphabet, how to put the alphabet together to find words. Words form sentences, sentences form paragraphs, and on the analogy could go. As a beginning chemistry student, we have to think about the basic building blocks of matter. When we understand how atoms come together to form compounds, we begin to understand about bonding. And those are very first steps as atoms come together to make compounds, much more stable arrangements for their electrons. We then learn how to name them based on the way they've organized themselves. So we start small. We start with introducing you to what atoms are and how atoms arrange themselves on the periodic table. Understanding the periodic table and how atoms are placed on there lets us predict how compounds form. When atoms come together to make compounds, they do so by following very strict rules, forming ionic bonds or covalent bonds, forming ionic compounds or molecular compounds. And each time they do so, we have a different set of rules for naming them. Let's begin in our note pack by writing down the definition of an atom. It is indeed the smallest particle of an element that retains the properties of that element. You know you have the ability to pause this video at any time to catch your writing up and then hit play when ready. So if you think I'm going too fast, that's the beauty of a video lesson versus a live lecture. You're in control of the pace. I'll repeat what's an atom and talk more. The smallest particle of an element that cannot be broken down by ordinary chemical properties. Elements are built of atoms. I can point to the periodic table and show you all kinds of different elements. And when I do so, I'm referring to the basic building block, like a Lego block that comes together to form larger structures. Atoms come together to form larger structures called compounds. We know, probably from our background knowledge, that atoms themselves are built of smaller subatomic particles. Ever hear of the terms protons, neutrons, and electrons? We know that there's two particles that reside inside of the central core of an atom, known as a nucleus. The first of those are called protons. Inside of the nucleus are these positively charged particles. Inside of the nucleus also lies neutral particles known as neutrons. So I envision this densely populated area of an atom, the central core known as a nucleus. And placed inside of the nucleus are little particles that carry charges and little particles that do not carry charges. Positively charged protons and neutrally charged neutrons. Well, what else is making up an atom? These are the negative electrons outside of the nucleus, orbiting around, creating such a fast velocity that they appear to be a cloud outside of the nucleus. Electrons are the negatively charged particles that orbit around the nucleus in very specific energy levels. Oftentimes, it's easiest for us as beginning chemistry students to think of an atom as a solar system model. Niels Bohr, a chemist back in the mid to late 1900s, so I'm thinking about 1940, 1950, this research was going on, was working along with his professor, Ernest Rutherford, and these are names that we'll talk a little bit more about, but Niels Bohr is credited with giving us that solar system model, where the nucleus of an atom is inside this densely populated area of electron cloud. So the center of an atom where the protons and neutrons are, very heavy, very small, but that's where the most of the mass is located in an atom. It's really what gives the entire atom its weight. These tiny little particles known as electrons reside outside of this very heavy, dense center known as the nucleus. Here's what I always think of when I give an analogy about weights of these particles. Protons and neutrons are very, very heavy, and yet when they're inside the nucleus, they occupy the tiniest amount of the whole volume of an atom. Electrons are so tiny compared to the protons and neutrons, they hardly contribute any weight to the atom at all. Oh, they're in the atom, but they're such a negligible mass. Imagine taking a big German Shepherd to the vet, and the vet, as always, asks you to place that puppy up on the weighing scale. Would that dog or that puppy, that German Shepherd, weigh differently with or without fleas? Well, obviously fleas have mass, but comparatively to the size of a large German Shepherd, the fleas do not contribute much to the overall mass. We say that the fleas have a negligible mass. The same can be thought of for electrons. Electrons are indeed part of an atomic structure, but their weight is so insignificant to the overall weight of the nucleus, we don't really bother counting it when we weigh an atom. The nucleus is very heavy compared to the electrons. We have this center region known as the nucleus. Well, what are the electron energy levels? Things that are known as orbitals, the little rings, if you will, placed around the nucleus in our solar system model. Within these very specific rings around the nucleus, electrons are found moving. They're very, very, very fast. They exist in certain energy levels, moving around so fast they create this cloud-like appearance. Energy levels are the specific areas in which we find electrons. They exist in certain fixed energy levels, and we'll discuss that a whole lot more. Continuing some talk about atoms, we know that in nature, atoms are identified by their number of protons. A proton gives its atom its identity. Atomic number off of our periodic table gives me the identity of an atom by telling me how many protons there are. However, the same type of atom could vary by weight. And if they're varying by weight, they must have different number of neutrons. This is a very important note. Maybe I'd encourage you to add it on. Call it a margin note. The term isotopes. These are atoms of the same element that differ by the number of neutrons. Add this part on. They have the same protons, but different neutrons. Protons give an atom its identity. We cannot change the number of protons and maintain the original identity of an element. Isotopes in nature are indeed the same element, but by varying the number of neutrons packed inside of the nucleus, we're varying the weight of that particular element. Neutron number can change without changing identity. And here's this term again I said just a moment ago, the atomic number. This is the number of protons found inside the nucleus of an atom. It does indeed give that atom its identity. If I were to look at my periodic table and find the elements, I'd encourage you to find yours. You should have your periodic table out. I know you wouldn't leave home without it. If I find the first element on the periodic table with a symbol H, we know it's called hydrogen. There's a number in there, and it's always a whole number, an integer placed on the periodic table. Hydrogen is number 1. It has 1 proton. Element number 2 is known as helium. Its atomic number of 2 is telling me it has 2 protons. Lithium is element number 3. Therefore, I now know it has 3 protons. The identity of an element can be determined by simply knowing how many protons it has, because the proton indeed matches the number, its atomic number, on the periodic table. Now, the mass number is the weight of the nucleus of an atom. How many protons and neutrons are added together gives us its mass number. If I have an atom that has 2 protons and 2 neutrons, the total number of particles inside the nucleus is 4. I would have a mass number of 4. That, by the way, is helium. These mass numbers do have a unit associated with it, as all scalar quantities do, a number with a unit. The unit is known as an AMU. That stands for an atomic mass unit. Atomic mass units are always whole numbers. Would you please write that down underneath this area as well? They are always whole numbers because I'm adding particles. There's no such thing as a half of a proton or a quarter of a neutron. I'm adding the number of protons and neutrons together, and therefore I'll always get a whole number. Now you might ask, why oh why do I see decimal points then on the periodic table? If mass numbers are whole numbers, why do I have decimals on the periodic table? And the answer lies with a word coming up, just not yet, but coming soon. The term is called atomic mass. If you wanted to write it and say it early, that's okay. The atomic mass is what I find on the periodic table. And what that is, friends, it's the weighted average of all the isotopes we find for that element in nature. Because I'm averaging a variety of different weights, now you can see why we end with decimals. Mass numbers are always whole numbers. They are not found on the periodic table. Write that down. I encourage you to take good notes. The other word is atomic mass. Atomic mass are the weighted averages of all isotopes found in nature for that particular element. And because we're averaging a variety of weights, now you can see why on the periodic table you find decimal places. We'll talk again more and more about isotopes. Let's see what we know, what we remember, looking at a few series of models of atoms. If you think about your solar system model, this will be great. Now, on your periodic table, that's a tool. We need to find some things. I see I have helium with a -4. See how we have helium -4. The symbol is telling me that it's helium. The mass number is 4. So the -4 is telling you how many total particles. But let's be even smarter. Find on your periodic table helium, its symbol He. The mass number 4 goes up high, and the atomic number goes down low. Let's be clear of our standard notation. Standard notation is the way that a chemist will show a reader what is the mass number and the atomic number for a particular isotope of an element. The symbol is written He. This is known as an atomic symbol. To the left of the symbol, up high, we place the mass number. Remember that those are always whole numbers. Down low, we have the atomic number. The very definition of the atomic number tells me the number of protons. So if I want to consider drawing a very simple model of helium, I start by placing just a circle to represent what I'll call the nucleus of our atom. Atomic number tells me protons. That's its very definition. So by seeing this atomic number of 2, I had to look it up on my periodic table, I'm going to show that there's 2 positive protons inside of my nucleus. And let me chat a little bit about the symbols I'm using. Depending upon instructors you might have had in your past, you might have been told to draw little positive signs to represent 2 positive protons. Some of us were even told to put them inside of a little circle to denote little particles. I find that that gets tedious, and it's very difficult to grade. In my class, I want you to tell me the number of protons by placing the number, the little sign P for protons, and now I know it's a positive charge. 2P positive shows me 2 protons. It's that easy. What else do we know? Well, we know that the mass number is 4. And literally, this is telling me the sum of the protons and the neutrons together. The mass number tells me how heavy the nucleus is. If there's 4 total particles, I see that right here, and 2 of them I know are from protons, I'm going to subtract. 4 minus 2 tells me there's 2 neutral neutrons. We've now placed the subnuclear particles, protons and neutrons. We have electrons to place. Perhaps somewhere in your journey of class you remember in the first energy level there's 2 electrons and then it gets full. In the second energy level you can place up to 8 electrons before it is full. In the third energy level, you can place up to 8 more electrons before it is full. We can seriously talk why in just a moment, but for now I'm just making us perhaps explain for the first time, some background knowledge. One other statement we should be clear on, atoms are always neutral. And the reason I'm bringing that up, because if I know the number of positive protons, what I'm also being given is the number of electrons, because indeed the positive protons are going to neutralize the charge of the number of electrons. Now what I like to do is to simply draw the first energy level as a half shell. That's going to save me, instead of drawing a big circle around it, such as this, and then I draw another circle such as this. Sometimes I get these structures that end up so large, our paper gets quite messy. So I'm going to ask that we don't do it that way, but instead we'll simply, let me redraw, 2 positive protons, 2 neutral neutrons inside of a nucleus. And again, I don't want dots for electrons. I want to just simply see that there are 2 electrons in the first energy level. We've just drawn a simple model of helium. The mass weighs 4. I can count the number of particles inside 2 positive protons with 2 neutral neutrons gives me a mass number of 4. The number of protons is indeed neutralizing the number of electrons. Let's process a moment before we move on. What information have we gleaned? We were given a symbol, He, with a little there, it was telling us it weighs 4. Mass number is 4. We looked up its atomic number 2. We wrote what was called the standard notation of helium. The symbol, and to the left, mass number, atomic number. And from there, we drew a simple model of an atom of helium. Let's continue that same process, but this time let's consider something much larger. From your periodic table, let's find calcium. We need to know some things about calcium before we can draw it. We would need to know its atomic number and its symbol. Calcium has a symbol Ca. The hyphen after the name from our little diagram here says 40. Its mass number is 40. Did you find it yet on the periodic table? Its atomic number is 20. 40 over 20. Again, this is what's called the standard notation. The standard notation is the symbol with the mass number up high and the atomic number down low. Those are called superscripts and subscripts. Let's draw a circle to represent our nucleus. Inside the nucleus, we now know how many protons it has because the atomic number has been identified. As soon as I found calcium, located it on the periodic table, we saw that it is number 20. Number 20 is telling us, oh, that has 20 protons. If the entire mass of the nucleus, the mass number, adds to 40, and we've already accounted for 20 of the 40 particles, 40 minus 20 is showing that we also have 20 neutral neutrons. The mass number is giving me the sum of all the nuclear particles, protons and neutrons. 20 positive particles plus 20 more neutral particles gives me an entire mass of 40. But how do the electrons arrange themselves? Remember what we reviewed a moment ago? We'll have 20 electrons to place by the time we're done. The first energy level can at most hold 2 electrons before it's full. The reason? Period 1 on the periodic table only has 2 elements, hydrogen, helium. It's full. When I reach the end of the row, hydrogen, helium, I've placed 2 electrons. I reach the end, I go down a level. I hit the second row on the periodic table. The second row denotes this second energy level, the ring around our nucleus. How many elements are there in row 2 of the periodic table? Well, I count lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. If you followed with me on your periodic table, you counted 8 elements. The second energy level can only have 8 electrons. There's 8 positions on the periodic table in row 2. What about row 3? Our third energy level coming from period 3 from the periodic table. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. If you counted with me on your periodic table, we've just listed 8 more elements. Row 3, ring 3 has 8 positions. Then it's full. We hit the end of the road. When we go down a column or go down a row, we hit the 4th energy level. But let's count. We know we had 20 to place. 2 plus 8 is 10, plus 8 more is 18. We only have 2 to place. The last 2 electrons are placed in the 4th energy level. Boy, we can be really smart about this. Calcium lives in period 4. How many energy levels did we just draw? We just drew 4 energy levels. Coincidence? I think not. E-N-E-R-G-U-I. Sorry about that misspelling. Energy level. How many electrons are in the outermost orbital? I see 2. Coincidence? I think not. The group 2, capital A, we'll talk more about the organization of group A's versus group B's. A's are the tall columns. If you clearly look at your periodic table, calcium's group number is group 2A. How many electrons are in the outermost ring? 2. That's why calcium lives where it lives. The period tells me how many orbitals, how many shells, how many rings am I going to draw. The group number gives me insight into how many electrons are placed in the outermost energy level. Our basic models of atoms are nice models for predicting bonding, but I want to be clear, friends, these really are not the way atoms look like. Atoms do not look like solar systems, but for beginning chemistry students, it is a great model, a very great model, to predict bonding. But someday when we advance just a little further, we'll talk about the quantum mechanical model and the SPDF sublevels of an atom. Friends, the truth of the matter is when we draw a first energy level, it's actually an S-shaped cloud, spherical. It's three-dimensional. That electron is not in a flat shell, it's a spherical shape. Second energy level, and so forth. I want us to start just seeding a little bit about energy levels having sublevels in the quantum mechanical model. It's not part of this unit, but I just need you to be aware this is a great model, but it's not what atoms look like. Let's review together some of the highlights from our lesson. What did we say for the subatomic particle that gave an atom its identity? Boy, I bet you wrote that in your margin note. I bet you did. I bet you wrote down that it was the proton. The subatomic particle. It comes from the atomic number. Hey, what element, what atom has 3 protons? Well, who's number 3 on the chart? Well, that's lithium. Suppose we had an atom identified as platinum, 195. See that 195? What does that number represent? We were just practicing with helium and calcium. We know that it represents what's called its mass number. The 195 is its mass number. We now know that that's the protons and the neutral neutrons added together. Now I have to be a little detective. How many protons? Well, I don't know until I pull out my periodic table. Do that with me. What number is platinum? It might be helpful to know its symbol is PT. Search for it, PT. Kind of in the center, around gold and silver. Did you see him yet? He's number 78. Mercury, whoops, is his neighbor there. Let's see, 78 is its atomic number. I wouldn't have known that without my periodic table tool. How many neutrons? Well, if I know the mass number as 195, we just found that 78 of those 195 particles are coming from protons. I have to subtract the mass number from the proton number. It looks to be 117 neutrons. How many electrons? Well, I know that protons and electrons are the same number because atoms are neutral. So when we found the atomic number of 78 and identified 78 positive protons, we also identified that they would contain 78 negative electrons. Our next screen will ask, how are isotopes of the same element alike, and how are they different? By our very definition of isotopes, I know that they differ by the number of neutrons, but they always have the same number of protons. If protons give the atom its identity, I can change the neutrons, which by the way means that they would have different masses. The different mass number could be different, but it would end up being the same element. Let's emphasize that. Draw this with me. Suppose in nature we have an archaeological dig going on, and we'd like to know that how old a certain artifact is that an archaeologist has dug up from a site. Oftentimes they do what is called carbon-14 dating. We also know the most natural, abundant isotope of carbon is 12. Carbon, if I looked on the periodic table, has an average mass of 12.011. Most abundant isotope is 12. But in nature, once in a while, we find a second kind of carbon atom known as a carbon-14 atom. Do you see what is the same? The same atomic number. A same atomic number means that it has the same number of protons. But what's different about them? Well, what's different is the mass number, how heavy the nucleus is. Carbon-14 must have 8 neutrons, 14 minus 6. Carbon-12 must have 6 neutrons. Everything else is the same about those isotopes, except the neutrons. What would an argon atom look like? Argon. I'm not going to draw that, but I want you to. I can check it in your notepacks. Let me know when you've drawn it, and I'll come by and check it for you. What I'd like to do is to put a star on your notepad page. When I put a star on the end of your page 1, I know you've got it complete and correct and ready to go on. Stop the video, draw your argon 40, and then call me over.